Right now, a spacecraft launched before most people alive today were born is still moving, still transmitting, still crossing territory no human instrument has ever closely examined. Its signal, traveling at the speed of light, takes more than 22 hours to reach us. Nearly a full day for the fastest thing in the universe to cross the distance between that probe and the ground station waiting for its whisper. And that spacecraft has not even reached the edge. But here is what most people never stop to consider. We have not actually seen most of our own solar system. Beyond Neptune, beyond the last great planet, beyond the familiar map, lies a region so vast, so cold, and so resistant to every instrument we have ever built that our picture of it is less a map and more a guess. A careful guess, assembled from fragments and shadows and the occasional messenger falling inward from the dark, but a guess nonetheless. If that thought settles strangely, if the idea that our own home remains largely unknown to us feels like something worth sitting with for a while, do me a small favor and hit that like button and subscribe. It genuinely helps this channel keep making deep dives like this one. Get yourself comfortable. Let's begin. There is a version of the solar system most of us carry somewhere in memory. 8 planets arranged in a neat procession outward from the sun. Mercury closest, baked and airless. Then Venus, then Earth, then Mars, a little red and cold. Then the great gas worlds. Jupiter enormous and banded, Saturn ringed and luminous, Uranus tilted strangely on its axis, Neptune distant and blue and quiet at the edge. A clean picture, orderly, the kind of diagram that fits comfortably on a classroom wall and stays there for decades without anyone questioning whether it is complete. It is not complete. It never was. But for most of human history, that incompleteness was invisible to us because the tools required to see beyond it did not exist, and the distances involved were so immense that imagination itself tended to stop at the last known planet and call that the boundary. Neptune was the wall. Everything beyond it was silence, emptiness, a kind of cosmic margin that the map simply left blank. What we know now is that the blank margin is not empty. It is full of objects and distances and structures so enormous they strain the vocabulary of measurement. But knowing that it is full is not the same as knowing what it contains. And this distinction, quiet as it seems, is the thing this story keeps returning to. To understand why the outer solar system remains so poorly known, it helps to begin at the moment the outer solar system became known at all. Not the full picture, which we still do not have, but the first tentative outlines. The first time human beings extended the map past what the naked eye could reach. Uranus was discovered in 1781 by the British astronomer William Herschel, working in his garden in Bath with a telescope he had built himself. He was not looking for a planet. He was conducting a systematic survey of the sky, cataloging stars, when he noticed an object that behaved differently from everything around it. It moved. Over successive nights, it shifted position against the background stars in a way that no fixed star would. Herschel initially thought it might be a comet, but the object had no tail, no coma, no diffuse glow. It was round. It was steady. It was a world. The discovery doubled the known size of the solar system in a single evening. Saturn, the outermost planet visible to the naked eye, orbits the Sun at roughly 886 million miles. Uranus orbits at nearly twice that distance, around 1.8 billion miles. The solar system was suddenly, overnight, twice as large as anyone had believed. And it had been there all along, circling quietly, visible through any decent telescope, simply never identified for what it was. Neptune arrived differently. It was not stumbled upon. It was calculated into existence. By the mid-1800s, astronomers had been tracking Uranus long enough to notice that its orbit was not quite right. The planet was not where the mathematics of gravity said it should be. Something was pulling it, something massive, orbiting farther out, tugging at Uranus with its gravity and bending the path it traveled. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently worked through the equations and predicted where the unseen world should be. In September 1846, the German astronomer Johann Galle pointed his telescope at the coordinates Le Verrier had sent him and found Neptune within the first hour of looking, less than 1 degree from where the mathematics had placed it. This was one of the great triumphs of theoretical science. A planet found not by accident, not by extended search, but by pure calculation. The laws of gravity were so well understood that an invisible world could be located from a desk in Paris, using only pencil and numbers. Neptune sits roughly 2.8 billion miles from the Sun. At that distance, the Sun appears not as the blazing disk we know, but as an intensely bright star. Brilliant, certainly, far brighter than anything else in the sky, but a point of light rather than a presence. The warmth that floods an afternoon here is imperceptible out there. Neptune's surface temperature hovers around negative 350 degrees Fahrenheit. It is cold in a way that ordinary language was not designed to describe. Cold as a permanent condition, not a season. Cold as the default state of a world that has never been otherwise. Light, crossing from the Sun to Neptune, takes roughly 4 hours and 10 minutes. To put that in human terms, in the time it takes the Sun's light to reach Neptune, you could sleep a full night and still have hours remaining before the first photon completed its crossing. That same light reaches Earth in 8 minutes. The ratio tells you something about the distances involved. Neptune is not merely far. It is in a different category of far from anything we experience or intuitively grasp. The only spacecraft ever to visit Neptune was Voyager 2. Launched in 1977, it reached Neptune in August 1989, 12 years after leaving Earth. It did not stop. It could not. It had no mechanism for slowing itself into orbit at that point in its journey. No fuel remaining for anything but the long outward drift that would follow. It flew past at roughly 61,000 miles per hour, cameras running, instruments collecting everything they could in the narrow window of closest approach. Consider what that encounter looked like from a distance. A machine the size of a small car, assembled by human hands in a facility in Pasadena, crossing 2.8 billion miles over 12 years to spend a few hours near a world it could never touch. The data it collected traveled back to Earth at the speed of light, taking 4 hours to arrive. 4 hours for the signal to cross the same distance the spacecraft had spent more than a decade traversing. Engineers on the ground received images of Neptune's atmosphere, its storm systems, its pale and unexpected blue. They saw a world in motion, winds moving faster than any on Earth, cloud bands stretched across the face of a planet that receives so little sunlight It should by rights be nearly static. Neptune was alive in ways no one had fully anticipated. And then Voyager 2 continued outward. The encounter lasted hours. The images it returned, those photographs of a world wrapped in deep azure, of the large dark storm churning in Neptune's southern hemisphere, of the moon, Triton hanging cold and pinkish against the void. Those images are still the best close-up pictures we have. More than 3 decades later, no successor mission has arrived. Neptune has been visited once, briefly, by a spacecraft that could not linger. What we know of it in detail fits inside a few hours of flyby data collected before anyone alive today had finished primary school. What this means in practice is that our knowledge of Neptune itself, the last great planet, the outermost member of the familiar family, is thinner than our knowledge of Mars, or Jupiter, or Saturn, worlds that have been orbited and probed and studied across decades of sustained observation. Neptune we glimpsed, Neptune we photographed from a passing window, and Neptune, compared to what lies beyond it, is the familiar part. Neptune is the known shore. Beyond it, the map changes character entirely. It stops being a record of confirmed, measured, understood things and becomes something more tentative. A collection of inferences, a set of orbital tracks for objects detected but never visited, populations estimated but never counted, structures theorized but never directly observed. The solar system beyond Neptune is real. Its contents are as physical, as present, as measurable in principle as anything closer to the sun. But our knowledge of it is not the confident knowledge we have of the inner planets. It is careful, provisional, assembled from fragments and the occasional fortunate alignment of a distant object against a background star. For most of the 20th century, this did not trouble astronomers greatly. Neptune was the edge. What lay beyond it was assumed to be mostly empty, a vast dark interval between the solar system and the nearest stars. The planets ended, the emptiness began, and the map could be folded neatly at that boundary without much loss. This was a tidy picture, and tidiness is comfortable. We tend to hold on to tidy pictures longer than the evidence warrants, because replacing them requires admitting that the previous version was less a map and more a sketch, an outline drawn at the limits of what the available light could show. But sometime in the early 1990s, astronomers began to find things in the dark beyond Neptune. Small things, cold things, slow-moving points of light drifting against the background stars at distances that placed them clearly beyond the last planet. And each discovery made the blank margin a little less blank, made the comfortable picture a little less comfortable, made the question of what actually lies beyond Neptune a great deal more interesting and a great deal more difficult to answer than anyone had previously imagined. For most of the 20th century, the solar system ended at Neptune. That was the working assumption. Not a proven fact, not a carefully established certainty, but a default. The kind of belief that settles into a field of study when no one has yet found a reason to question it. The planets ended. The emptiness began, and somewhere unimaginably far beyond that emptiness, the nearest stars quietly burned. The assumption had a quiet logic to it. The outer planets, Jupiter, Saturn, Uranus, Neptune, had formed from the disk of gas and dust that surrounded the young sun roughly 4.5 billion years ago. As that disk thinned with distance, The material available for planet formation grew sparse. Neptune was the last place where enough material had gathered over enough time to assemble something large. Beyond it, the thinking went. There simply wasn't enough left over to amount to anything worth cataloging. What the thinking missed was that not amounting to a planet is not the same as not existing. In 1943, an Irish economist and amateur astronomer named Kenneth Edgeworth published a paper suggesting that the outer solar system might contain a population of small icy bodies, remnants of the original disk that had never gathered into a planet, spread across a broad ring beyond Neptune, too small and too scattered to be seen with the instruments of his time. His paper drew little attention. 8 years later, in 1951, the Dutch-American astronomer Gerard Kuiper independently proposed something similar: a flattened disk of primordial debris lying beyond Neptune, the frozen leftovers of solar system formation. Kuiper's version of the idea was somewhat different from Edgeworth's in its details, and he actually doubted the population still existed in significant numbers by his time. But his name attached itself to the concept, and the concept waited. It waited 40 years. On the night of August 30th, 1992, astronomers David Jewett and Jane Liu, working with a telescope on Mauna Kea in Hawaii, detected a faint, slow-moving object beyond Neptune. It was small. It was dark. It was cold. It sat at a distance of roughly 44 astronomical units from the Sun, 1 astronomical unit being the distance from Earth to the Sun, approximately 93 million miles, meaning this object orbited at more than 4 billion miles out. It was designated 1992 QB1. It had no atmosphere, no moons anyone could detect, no distinguishing features visible at that distance. It was, by any ordinary measure, unremarkable, but it was there, beyond Neptune, in the place the theories had said to look, and its existence transformed the blank margin on the map from an assumption of emptiness into a confirmed population waiting to be counted. What followed over the next 3 decades was a slow accumulation of similar discoveries, object after object, pulled from the background noise of sky surveys, each one adding a data point to the emerging portrait of a vast, sparse, ring-like region extending outward from roughly 30 astronomical units, just beyond Neptune's orbit, to perhaps 50 astronomical units. This region, named the Kuiper Belt in honor of the astronomer whose name had attached itself to the prediction, was not a band of dense material. It was nothing like the asteroid belt between Mars and Jupiter, which science fiction has so often rendered as a treacherous maze of tumbling rock. The Kuiper Belt is immense and extraordinarily sparse. Objects within it are separated by millions of miles on average. A spacecraft passing through it, as New Horizons did on its way to Pluto, would almost certainly never come close to any object it hadn't been specifically aimed toward. The emptiness between objects is the dominant feature, but the objects are there. To put the scale in human terms, the asteroid belt, that familiar ring between Mars and Jupiter, spans a region roughly 140 million miles wide. The Kuiper Belt spans a region more than 1 billion miles wide, at distances so far from the Sun that the journey there, even at the velocities achieved by our fastest spacecraft, takes not months but years. Decades. New Horizons, launched in January 2006, and the fastest spacecraft ever sent to the outer solar system, took 9.5 years to reach Pluto. 9.5 years of continuous travel at speeds that would carry you from New York to Los Angeles in roughly 3 minutes. Pluto sits near the inner edge of the Kuiper Belt. This is worth pausing on because Pluto occupied a peculiar position in the human imagination for 76 years. The lonely ninth planet, the small, cold world at the edge of everything, discovered in 1930 by a young astronomer named Clyde Tombaugh, who spent months blinking pairs of photographic plates looking for any point of light that shifted position between exposures. Tombaugh found it. He was 24 years old. The discovery made headlines around the world and gave the solar system its final member, or so it seemed. What the 1992 and subsequent discoveries revealed was that Pluto was not an oddity. It was not a lonely outlier parked at the edge of the known map. It was a resident of a vast population, one of the larger members of a family that likely numbers in the hundreds of thousands. The solar system had not ended at Neptune. It had merely changed character. The large, dense, gaseous worlds gave way to a different kind of territory. Smaller, icier, darker, slower, and enormously more numerous than anyone had understood when Pluto was named the ninth planet and the map was considered complete. The International Astronomical Union's 2006 decision to reclassify Pluto as a dwarf planet was, at its core, a recognition of this reality. Pluto had not changed. What had changed was the understanding of the population it belonged to. Calling Pluto a planet while refusing the same designation to dozens of similar or larger objects in the same region was no longer a coherent position. Eris, discovered in 2005, appeared at first to be larger than Pluto, a world in the same outer region, equally round, equally cold, equally remote. If Pluto was a planet, Eris was a planet. And if Eris was a planet, the catalog would need to grow considerably. The IAU drew a line. The line was imperfect and remains contested. But the reason it had to be drawn at all was that the outer solar system had turned out to be far more populated than the old map suggested. The Kuiper Belt, as currently understood, contains several thousand catalogued objects. But catalogued is not the same as counted. The surveys that have identified these objects are incomplete, deeply, fundamentally incomplete, in ways that matter enormously for understanding what the belt actually contains. Current estimates suggest there may be 100,000 or more objects larger than 100 kilometers across, roughly 60 miles in diameter, orbiting in the Kuiper Belt region. We have found a few thousand of them. The rest remain in the dark, moving slowly along their orbits, reflecting the dim and distant sunlight back into a sky that has not yet turned an instrument sensitive enough in their direction. And the belt may not end at 50 astronomical units, the way the simplest models suggest. The outer edge, if it has a clean edge at all, is poorly defined. There are objects in orbital configurations that place them beyond the classical Kuiper Belt, in a region called the scattered disk, where Neptune's gravitational influence has flung material onto elongated, tilted orbits that carry them far out and then back again over timescales of thousands or millions of years. The boundary between the Kuiper Belt and what lies beyond it is not a line. It is a gradient, a slow thinning of one kind of population into another, across distances so vast that the distinction between where one region ends and the next begins is more a matter of classification than of any physical boundary in space. What this means, quietly, is that the shore beyond Neptune has no clear edge. the map does not end cleanly. It fades. Objects become fewer. Orbits become stranger. Distances become harder to comprehend. And at some point, the familiar vocabulary of the solar system gives way to something less certain. A territory defined less by what has been found and more by what the models predict should be there, waiting in the cold and the dark for instruments we have not yet built. And the Kuiper Belt, vast and poorly counted as it is still the part we know best. It is still the lit margin of a much deeper darkness. For most of the 20th century, the solar system ended at Neptune. That was the working assumption. Not a proven fact, not a carefully established certainty, but a default, the kind of belief that settles into a field of study when no one has yet found a reason to question it. The planets ended, the emptiness began, and somewhere unimaginably far beyond that emptiness, the nearest stars quietly burned. The assumption had a quiet logic to it. The outer planets, Jupiter, Saturn, Uranus, Neptune, had formed from the disk of gas and dust that surrounded the young sun roughly 4.5 billion years ago. As that disk thinned with distance, the material available for planet formation grew sparse. Neptune was the last place where enough material had gathered, over enough time, to assemble something large. Beyond it, the thinking went. There simply wasn't enough left over to amount to anything worth cataloging. What the thinking missed was that not amounting to a planet is not the same as not existing. In 1943, an Irish economist and amateur astronomer named Kenneth Edgeworth published a paper suggesting that the outer solar system might contain a population of small, icy bodies, remnants of the original disk that had never gathered into a planet, spread across a broad ring beyond Neptune, too small and too scattered to be seen with the instruments of his time. His paper drew little attention. 8 years later, in 1951, the Dutch-American astronomer Gerard Kuiper independently proposed something similar. A flattened disk of primordial debris lying beyond Neptune, the frozen leftovers of solar system formation. Kuiper's version differed from Edgeworth's in its details, and he actually doubted the population still existed in significant numbers by his time. But his name attached itself to the concept, and the concept waited. It waited 40 years. On the night of August 30th, 1992, astronomers David Jowett and Jane Liu, working with a telescope on Mauna Kea in Hawaii, detected a faint, slow-moving object beyond Neptune. It was small. It was dark. It was cold. It sat at a distance of roughly 44 astronomical units from the Sun, 1 astronomical unit being the distance from Earth to the Sun, approximately 93 million miles, meaning this object orbited at more than 4 billion miles out. It was designated 1992 QB1. It had no atmosphere, no visible moons, no distinguishing features resolvable at that distance. It was, by any ordinary measure, unremarkable. But it was there, beyond Neptune, in the place the theories had said to look, and its existence transformed the blank margin on the map from an assumption of emptiness into a confirmed population waiting to be counted. What followed over the next 3 decades was a slow accumulation of similar discoveries. Object after object pulled from the background noise of sky surveys, each one adding a data point to the emerging portrait of a vast, sparse, ring-like region extending outward from roughly 30 astronomical units just beyond Neptune's orbit to perhaps 50 astronomical units. This region, named the Kuiper Belt, was not a band of dense material. It was nothing like the asteroid belt between Mars and Jupiter, which imagination has so often rendered as a treacherous maze of tumbling rock. The Kuiper Belt is immense and extraordinarily sparse. Objects within it are separated by millions of miles on average. A spacecraft passing through it would almost certainly never come close to any object it hadn't been specifically aimed toward. The emptiness between things is the dominant feature, but the things are there. To put the scale in human terms, the asteroid belt spans a region roughly 140 million miles wide. The Kuiper Belt spans a region more than 1 billion miles wide, at distances so far from the Sun that the journey there, even at the velocities achieved by our fastest spacecraft, takes not months, but years. Decades. New Horizons, launched in January 2006, and among the fastest spacecraft ever sent outward, took 9.5 years to reach Pluto. 9.5 years of continuous travel, covering roughly 3 billion miles, to reach the inner edge of the belt. Pluto sits near that inner edge. This is worth pausing on, because Pluto occupied a peculiar position in the human imagination for 76 years. The lonely ninth planet, the small cold world at the edge of everything, discovered in 1930 by a young astronomer named Clyde Tombaugh, who spent months blinking pairs of photographic plates, looking for any point of light that shifted position between exposures. Tombaugh found it. He was 24 years old. The discovery made headlines around the world and gave the solar system its final member, or so it seemed. What the 1992 and subsequent discoveries revealed was that Pluto was not an oddity. It was not a lonely outlier parked beyond the known map. It was a resident of a vast population, one of the larger members of a family that likely numbers in the hundreds of thousands. The solar system had not ended at Neptune. It had merely changed character. The large, dense, gaseous worlds gave way to a different kind of territory. Smaller, icier, darker, slower, and enormously more numerous than anyone had understood when Pluto was named the ninth planet, and the map was considered complete. The International Astronomical Union's 2006 decision to reclassify Pluto as a dwarf planet was, at its core, a recognition of this reality. Pluto had not changed. What had changed was the understanding of the population it belonged to. Calling Pluto a planet while refusing the same designation to dozens of similar or larger objects in the same region was no longer coherent. Eris, discovered in 2005, appeared at first to be larger than Pluto, a world in the same outer region, equally round, equally cold, equally remote. If Pluto was a planet, Eris was a planet. And if Eris was a planet, the catalog would need to expand considerably. The IAU drew a line. The line was imperfect and remains contested. But the reason it had to be drawn at all was that the outer solar system had turned out to be far more populated than the old map had ever suggested. The Kuiper Belt, as currently understood, contains several thousand cataloged objects. But cataloged is not the same as counted. The surveys that have identified these objects are incomplete, deeply, fundamentally incomplete, in ways that matter for understanding what the belt actually contains. Current estimates suggest there may be 100,000 or more objects larger than 100 kilometers across orbiting in the Kuiper Belt region. roughly 60 miles in diameter. We have found a few thousand of them. The rest remain in the dark, moving slowly along their long, cold orbits, reflecting the dim and distant sunlight back into a sky that has not yet turned a sensitive enough instrument in their direction. Beyond the classical belt lies a region called the scattered disk, a population of objects flung by Neptune's gravity onto elongated, tilted orbits that carry them far out from the sun and then back again over timescales of thousands or millions of years. These objects do not orbit in the same flattened plane as the classical belt. They are scattered, as the name suggests, into orbits that tip and stretch in ways that make them harder to find and harder to characterize. They occupy a zone that bleeds outward from the Kuiper Belt into something less defined, less populated, and less understood. And then there are the detached objects, bodies whose orbits are so elongated and so distant that Neptune's gravity cannot easily explain how they got there. Sedna is the most prominent of these. Discovered in 2003, Sedna follows an orbit that carries it from roughly 76 astronomical units at its closest approach to the Sun to perhaps 940 astronomical units at its farthest. Its orbital period is estimated at roughly 11,000 years. At its current position, it sits so far from the Sun that the temperature on its surface approaches negative 400 degrees Fahrenheit. It is one of the most distant objects in the solar system ever directly observed, and no current model of solar system dynamics fully explains the orbit it follows. Something, a passing star, an unseen planet, the gravitational influence of the early galactic environment, placed Sedna where it is. We do not know what. What Sedna represents, quietly, is the edge of the catalogued solar system dissolving into territory where our models begin to lose their grip. It is a data point that sits outside the expected distribution, an object that the map did not predict and cannot yet fully accommodate. And if Sedna exists in an orbit we struggle to explain, it is reasonable to ask how many similar objects orbit in the same distant region, too faint and too slow moving, and too far from our current survey coverage to have been found yet. The Kuiper Belt, vast and poorly counted as it is still the lit margin of a much deeper darkness. It is the shore, but the shore has no clean edge, and the ocean behind it has barely been glimpsed. But even this picture, incomplete as it is, was assembled through decades of careful observation, telescope time measured in thousands of hours, survey programs covering fractions of the sky. And the reason those surveys are incomplete is not ambition or funding alone. It is something more fundamental, something built into the physics of detection itself, something that grows more severe the farther out you look. There is a law in physics so simple it can be stated in a single sentence, and so consequential that it shapes everything we will ever know about the outer solar system. It is called the inverse square law of light, and what it says, in plain terms, is this: every time you double the distance between yourself and a source of light, the brightness of that light does not halve. It falls to 1/4. Double the distance again, and it falls to 1/16 of the original. The relationship is not linear. It is a cascade, a rapid, merciless dimming that accelerates with every additional increment of distance in a way that human intuition was never designed to track. For objects in the inner solar system, this law is a minor inconvenience. Mars at its farthest is still close enough that telescopes can resolve its surface features, track its dust storms, photograph its polar caps across the changing seasons. Jupiter is close enough that amateur astronomers with modest equipment can watch its moons move from night to night. Even Saturn, with its rings and its distance and its cold, is a bright and resolvable presence in any decent backyard telescope on a clear night. But the outer solar system is not the inner solar system, and the inverse square law does not care about the distinction. Consider a Kuiper Belt object sitting at 40 astronomical units from the Sun. That is 40 times the distance from Earth to the Sun, roughly 3.7 billion miles. Sunlight reaching that object is already enormously dimmer than sunlight reaching Earth. It has spread across a sphere 40 times larger in radius, meaning the intensity at that distance is 1,600 times weaker than what falls on our planet. The object absorbs that faint illumination and reflects a fraction of it back outward. That reflected light then has to travel back across 3.7 billion miles to reach a telescope on Earth, fading again according to the same inverse square law as it goes. What arrives at the telescope's mirror is not dim. It is nearly nothing, a whisper of photons, arriving at a rate so low that collecting enough of them to confirm the object's existence requires exposing the detector for minutes or hours, and even then, the signal barely rises above the background noise of the sky. What this means in practice is that detection is not simply a matter of pointing a telescope in the right direction. It is a matter of accumulating enough light, enough individual photons reflected from a dark, cold, distant surface to distinguish the object from the random fluctuations of the background. And the darker the object, the worse this problem becomes. Most Kuiper Belt objects are dark. Not dark the way a shadow is dark, but dark in the technical sense of having a low albedo, a low reflectivity. Fresh snow reflects roughly 80 to 90% of the sunlight that falls on it. The darkest Kuiper Belt objects reflect perhaps 4 or 5%. They are, in terms of their optical behavior, closer to charcoal than to ice, despite being composed largely of ices and frozen gases. Their surfaces have been processed over billions of years by cosmic radiation, by the slow bombardment of charged particles streaming out from the sun and from beyond the solar system, until the originally bright icy material has been converted into a dark, reddish, organic crust. A substance called tholin, a complex mixture of carbon and nitrogen compounds, coats many of these objects and absorbs light rather than returning it. To put this in human terms, finding a dark Kuiper Belt object at 40 astronomical units is roughly comparable to detecting a piece of charcoal the size of a city, sitting 3.7 billion miles away, lit by a flashlight 93 million miles from the charcoal, using a mirror the size of a large building. The photons exist. They are real, but they arrive so infrequently that distinguishing them from noise requires patience, precision, and instruments operating very near the limits of what current technology can achieve. And 40 astronomical units is still relatively close, as outer solar system distances go. The New Horizons mission gave us our most detailed picture of a Kuiper Belt object when it flew past Pluto in July 2015. The images it returned were extraordinary. A world of nitrogen ice plains, mountain ranges of water ice rising several miles above the surface, a hazy atmosphere tinted faintly blue, a heart-shaped region of frozen material so large it would span the distance from New York to Denver. Pluto turned out to be geologically complex in ways no one had fully anticipated. It was not the dead, featureless ball most models had predicted. It was alive, in the slow geological sense, shaped by processes that continued to operate across millions of years. But consider what it cost to obtain those images. New Horizons launched in January 2006. It traveled for 9.5 years, covering roughly 3 billion miles, before it spent approximately 72 hours near Pluto during closest approach. 72 hours of useful observation time at the end of nearly a decade of travel for a single object near the inner edge of the Kuiper Belt. The spacecraft then continued outward, and in January 2019 flew past a smaller object called Arrokoth, a contact binary, two lobes of reddish material gently joined together, at a distance of roughly 4 billion miles from the Sun. Arrokoth is among the most pristine objects ever examined by a spacecraft, untouched since the earliest days of solar system formation. The flyby lasted hours. Two objects, nearly 50 years of combined spacecraft development, launch, and travel time. A budget measured in hundreds of millions of dollars. Two objects in a population estimated to contain hundreds of thousands. This is not a criticism. It is a statement about the scale of the problem. In situ exploration of the Kuiper Belt, visiting objects directly, the way we visited the Moon or sent orbiters to Mars, is an extraordinary achievement when it happens. And it happens almost never because the distances and travel times involved place it at the outermost edge of what is currently possible. Each mission is a generational commitment. Each flyby is a single data point in a dataset that requires thousands. The alternative to visiting objects directly is to observe them from Earth or from Earth-orbiting telescopes, using the faint reflected light that reaches us across billions of miles. This is where the Sky Survey programs do their work. Systematic efforts to photograph large areas of the sky repeatedly, comparing images taken days or weeks apart to find objects that move against the fixed background of distant stars. Moving objects are solar system objects. Everything else stays still. The surveys have found thousands of Kuiper Belt objects this way, and the programs continue to improve. The Vera Rubin Observatory in Chile, when it reaches full operational capacity, will conduct the most comprehensive sky survey ever attempted, photographing the entire available sky every few nights with a camera so large and sensitive that it will detect objects far fainter than any previous survey could reach. Over its 10-year operational lifetime, it is expected to catalog tens of thousands of new solar system objects, including many in the outer regions that current surveys have missed entirely. But even the Vera Rubin Observatory has a limiting magnitude, a threshold of faintness below which objects simply cannot be detected, no matter how long the exposure. Objects smaller than a certain size, or darker than a certain reflectivity, or at distances greater than a certain range, will remain invisible to it. The survey will be the most complete picture of the outer solar system ever assembled. It will still be incomplete. And there is a layer beneath the detection problem that makes it still more difficult. Beyond roughly 50 to 60 astronomical units, the sky surveys that work well for the classical Kuiper Belt begin to lose their effectiveness not just because objects are fainter, but because they move more slowly. An object at 100 astronomical units orbits the sun so slowly that in the time between one survey image and the next, days, weeks, it barely moves against the background stars. Distinguishing it from a fixed background object requires either very precise measurements of very small shifts or a very long baseline of observations separated by months or years. The survey cadence that works for nearby objects fails for distant ones. The technique requires adjustment. The adjustment requires time, and the time required compounds with every additional increment of distance. The outer solar system does not simply hide its contents in darkness. It hides them in slowness, in the patient, almost imperceptible drift of objects so far away that they seem, to any instrument observing them over human timescales, to barely move at all. Distance swallows them, not all at once, not dramatically, but gradually, incrementally, in the quiet way that fog swallows a landscape, object by object, detail by detail, until what remains visible is only the nearest edge of something whose full extent lies beyond the reach of the light we can collect. And the discovery problem, as fundamental as it is only part of the story, because what we cannot detect is one kind of blindness. There is another kind, one that emerges not from the physics of light and distance, but from the way science constructs its categories, draws its boundaries, and decides what counts as known. That blindness is, in some ways, harder to correct. In the summer of 2006, the International Astronomical Union held its General Assembly in Prague. Several thousand astronomers had gathered from around the world, as they do every 3 years, to present research, attend lectures, and conduct the administrative business of the profession. Most of the sessions were technical. Most of the votes were procedural. But one vote, taken on the final day of the assembly, produced headlines in newspapers that do not normally cover astronomy at all. By a show of hands, a small fraction of the total IAU membership, those who happened to still be present on the last afternoon of a long conference, Pluto was reclassified. It was no longer a planet. It was, under a new definitional framework, a dwarf planet. The solar system had 8 members where it had previously had 9. The public response was, by the standards of scientific taxonomy, remarkable. People were upset. Not mildly puzzled or mildly interested, upset. Letters were written. Petitions circulated. Several state legislatures passed resolutions declaring that Pluto remained a planet within their borders, a gesture that accomplished nothing physically, but communicated something real about how attached human beings become to the maps they grow up with. Children who had memorized the 9 planets felt, in some genuine sense, that something had been taken from them. A world they had known had been reclassified out of existence. The solar system had been edited. What the response revealed, more than any scientific insight, was the depth of the confusion between a map and the territory it describes. Pluto had not changed. Its orbit remained what it had always been, an elongated ellipse tilted relative to the plane of the other planets, carrying it from inside Neptune's orbit at its closest to roughly 49 astronomical units at its farthest. Its size remained what it had always been, roughly 1,473 miles in diameter, smaller than Earth's moon, smaller than 7 other moons in the solar system. Its composition remained what it had always been, a mixture of rock and ice, colder than any inner planet, orbiting in the darkness of the outer solar system alongside a growing population of similar objects. None of this changed on the day of the vote. The universe did not reorganize itself to reflect the IAU's decision. What changed was the category. And the category had changed because the population it was meant to describe had turned out to be far larger and far more complex than anyone had understood when Pluto was first named and placed alone at the edge of the known map. The cascade began in the 1990s. As sky surveys improved and astronomers began finding Kuiper Belt objects in earnest, it became clear that Pluto was not a solitary oddity, but a prominent member of a vast family. Quaoar, discovered in 2002, was roughly half Pluto's diameter. Sedna, found in 2003, followed its strange, elongated orbit far beyond the classical belt. Then in 2005 came Eris, discovered by Mike Brown and his team at Caltech, initially measuring slightly larger than Pluto in some estimates, orbiting in a highly inclined path that carried it far out into the scattered disk. Eris was, for a time, referred to in the press as the 10th planet. The solar system was growing again, but the logic could not hold. If Eris was a planet, and Quaoar was potentially a planet, and Sedna was potentially a planet, and the surveys were finding new large Kuiper Belt objects regularly, then the solar system's planet count was not 9 and not 10, but potentially dozens, with more to be discovered as instruments improved. The category of planet was either going to expand to include a large and growing population of outer solar system bodies, or it was going to be redefined in a way that excluded them. The IAU chose redefinition. The new definition required a planet to do 3 things. It had to orbit the sun. It had to have sufficient mass for gravity to pull it into a roughly spherical shape. And it had to have cleared the neighborhood around its orbit of other debris, to have gravitationally dominated its orbital zone over the age of the solar system, either by absorbing smaller objects, ejecting them, or capturing them as moons. Pluto failed the third criterion. Its orbital zone, the broad region of the Kuiper Belt through which it travels, contains thousands of other objects. Pluto shares its neighborhood. It has not cleared it. The definition was immediately contested and remains contested today. Critics pointed out that the clearing criterion was poorly defined, that Earth itself, under a strict application of the same logic, had not cleared its orbital neighborhood of all debris, given the continued presence of near-Earth asteroids. Others argued that the definition was geophysical nonsense, that what made an object planet-like was its internal structure and geology, not its orbital dominance, and that Pluto, with its nitrogen ice plains and mountain ranges and hazy atmosphere, was more planet-like in any meaningful sense than many objects that met the IAU's criteria. The debate did not end in Prague. It moved into journals and conferences and occasional op-eds, where it continues, quietly, to this day. But the scientific merit of any particular definition is, for the purposes of this story, almost beside the point. What matters is what the debate revealed. It revealed that our categories for the outer solar system were built on an incomplete sample. The 9-planet model was not wrong because someone made an error. It was incomplete because the instruments needed to see the full population did not exist when the model was constructed. Pluto was classified as a planet in 1930, because it was the only object of its kind that anyone had found. It appeared unique because the technology required to find its neighbors had not yet been invented. The category was drawn around a single data point and assumed to be complete. This is a pattern that repeats throughout the history of outer solar system science. A region is observed at the limit of available instruments. A model is built from what is visible. The model is treated as a description of reality rather than a description of what current instruments can see. And then, when better instruments arrive, the model turns out to have been a portrait of its own limitations rather than a portrait of the territory. Sedna is the clearest current example of this pattern continuing. Discovered in 2003, it sits in an orbit so distant and so elongated that it defies easy explanation within the standard models of solar system formation. At its closest approach to the Sun, it is still roughly 76 astronomical units out, far beyond the classical Kuiper Belt. At its farthest, it retreats to nearly 1,000 astronomical units, a distance so immense that light from the Sun takes more than 5 days to reach it. Its surface temperature is among the coldest of any known solar system object, and its orbital period, the time it takes to complete one circuit of the Sun, is approximately 11,400 years. The last time Sedna was at this point in its orbit, the most recent ice age had not yet ended and anatomically modern humans had not yet reached the Americas. No known mechanism fully accounts for Sedna's orbit. The leading hypotheses involve a passing star in the early solar system, perturbing objects in the outer regions, or the gravitational influence of an as yet undetected massive body, the hypothetical Planet 9, pulling distant objects into unusual configurations. Neither hypothesis has been confirmed. Sedna sits in its strange orbit as a question the models cannot yet answer, a data point that the current map cannot fully accommodate. And if Sedna exists in an orbit that our models struggle to explain, it is reasonable to ask how many similar objects follow similar paths in the same distant region, too faint and too slow-moving to have appeared in any survey yet conducted. Sedna was found almost by accident during a survey that happened to be sensitive enough and pointed in the right direction at the right time. The outer solar system is large. Surveys cover fractions of it. The objects that happen to fall within survey footprints, at distances close enough to reflect detectable light, in orbits that bring them near enough to perihelion during the survey's operational window. These are the objects we find. They are a sample. How representative the sample is of the full population is a question we cannot yet answer, because answering it would require knowing the full population, which requires instruments and survey coverage we do not yet have. The 9 planets debate was, in the end, an argument about a map drawn from an incomplete survey of a territory that turned out to be far larger and far more varied than the map suggested. The reclassification of Pluto was not the end of that argument. It was a moment in the middle of it, a recognition that the old map was no longer adequate, followed by a first attempt to draw a better one, using categories that may themselves prove inadequate as surveys improve and the true shape of the outer solar system slowly comes into focus. Slowly, over decades, using instruments that are always, in some measure, just barely not powerful enough. And within all of this, the incomplete surveys, the contested categories, the objects that defy existing models, there is a signal, a pattern in the orbital data of the most distant known objects that some astronomers believe points towards something specific. Something large, something cold and dark and orbiting so far out that it has never once reflected enough light to register on any detector ever built. Something that may be shaping the outer solar system from a distance, the way Neptune shaped Uranus's orbit 2 centuries ago, not yet seen, but perhaps already felt. In January 2016, 2 planetary scientists at the California Institute of Technology published a paper that did something unusual in modern astronomy. It did not announce a discovery. It announced an absence, a specific, mathematically described absence, and argued that the absence itself was evidence of something large hiding in the outer dark. Konstantin Batygin and Mike Brown, the same Mike Brown whose team had found Eris a decade earlier, the discovery that set in motion the reclassification of Pluto, had been studying the orbital characteristics of a small group of extreme trans-Neptunian objects. These were bodies orbiting the Sun at distances so great that Neptune's gravity had little practical influence on them. Objects in the scattered disk and beyond, following elongated paths that carried them far out into the darkness and then, over thousands of years, back again toward the inner solar system. When Batygin and Brown examined the orientations of these distant orbits, the directions in which their elongated paths pointed, the angles at which they tilted relative to the plane of the solar system, they found something that the standard models of solar system dynamics did not predict. The orbits were clustered, not randomly distributed across the sky, as they should be if the objects were simply drifting under the accumulated gravitational influence of the known planets and the general pull of the galaxy. They were pointing disproportionately in the same general direction. 6 of the most distant known objects had orbits that aligned in a way that had roughly a 1 in 10,000 probability of occurring by chance. The clustering was not absolute, not geometrically perfect, but it was statistically striking. Something appeared to be organizing these orbits. Something appeared to be herding them, the way a shepherd's presence shapes the movement of a flock, without the flock necessarily being aware of the shepherd. Batygin and Brown ran simulations. They tested various configurations of known planets and known gravitational influences to see if any combination could produce the observed clustering without invoking an additional body. None could. They then asked what kind of object, placed where in the solar system, would produce the clustering they observed. The answer that emerged from the simulations was specific: a planet roughly 5 to 10 times the mass of Earth, orbiting the Sun at a distance of perhaps 400 to 800 astronomical units, following an elongated orbit inclined relative to the plane of the solar system, with a period of perhaps 10,000 to 20,000 years. In simple terms, a planet the size of Neptune, or slightly smaller, orbiting the Sun at a distance so extreme that it completes one circuit every 10 to 20,000 years, currently sitting somewhere in the outer darkness, at a distance that light from the Sun takes days to cross. This object, if it exists, has been named Planet 9. It has not been found. It has not been photographed. It has not produced a single confirmed detection in any survey ever conducted. Its existence rests entirely on the statistical behavior of a small group of other objects whose orbits appear to be influenced by something that cannot itself be seen. It is, in the most literal sense, a ghost in the data, present in the mathematics, absent from the sky. The search for Planet 9 has been underway in various forms since the 2016 paper. Dedicated telescope programs have scanned the regions of sky where the orbital models suggest it is most likely to be found. Machine learning algorithms have been applied to existing survey data, looking for slow-moving points of light that human reviewers might have missed. The Vera Rubin Observatory, when it reaches full operational capacity, will conduct a survey sensitive enough to detect a Neptune-sized object at the distances proposed for Planet 9. If Planet 9 falls within its survey footprint, and if the object's reflectivity is within the expected range. None of these searches have found it. This is not, by itself, surprising. Consider the numbers. Planet 9, if it exists at its proposed distance, reflects an extraordinarily small amount of sunlight. At 600 astronomical units, roughly the midpoint of the proposed range, a Neptune mass object would appear as one of the faintest points of light in the sky, indistinguishable at first glance from the billions of background stars and galaxies that fill every deep sky image. Finding it requires knowing approximately where to look, having a detector sensitive enough to record that faint reflection, and observing the same region of sky on multiple occasions, separated by weeks or months to detect the object's slow movement against the background. The movement at that distance is extraordinarily slow. An object at 600 astronomical units orbiting the Sun over 15,000 years moves across the sky at a rate so gradual that distinguishing it from a fixed background object requires months of baseline observation, at minimum. To put this in human terms, if Planet 9 exists and is sitting near the farther end of its proposed orbit, it is dimmer than roughly 99.9% of the objects in a deep sky survey image. It moves more slowly across the background sky than the hour hand of a clock moves across a clock face. Finding it is not a matter of pointing a telescope in roughly the right direction and looking. It is a matter of conducting a systematic, sensitive, multi-epoch survey of a significant fraction of the entire sky, and then carefully examining the resulting data for an object whose defining characteristic is its reluctance to be found. And there is a further complication. The case for Planet 9's existence rests on the orbital clustering of a small number of extreme trans-Neptunian objects. But that clustering may itself be an artifact of observational bias. The surveys that discovered these objects were not uniformly distributed across the sky. They were pointed preferentially at certain regions that happened for various practical reasons related to telescope scheduling and sky conditions and the geometry of the search programs to overlap with the same general area of the sky. If the surveys that found the clustered objects were themselves biased toward one region of sky, the apparent clustering of the orbits might reflect the bias of the surveys rather than the influence of an unseen planet. This is the central tension in the Planet 9 debate. The signal might be real. The clustering might reflect a genuine gravitational influence, a large unseen body organizing the orbits of distant objects the way Neptune organized Uranus's orbit 2 centuries ago. Or the signal might be an artifact, a pattern that appears in the data, not because it exists in nature, but because the surveys were incomplete in a specific, directionally biased way. Both possibilities are consistent with the current data. Neither has been ruled out. The astronomers who support the Planet 9 hypothesis argue that the clustering is too pronounced to be explained by survey bias alone. and that the simulations showing how a large outer planet could produce the observed distribution are persuasive. The skeptics argue that the sample of extreme trans-Neptunian objects is too small, fewer than 20 objects with well-characterized orbits in the relevant population, to draw statistically robust conclusions, and that as surveys expand and more objects are found, the apparent clustering may dissolve. What is certain is that the solar system's outermost regions contain at least one object, Sedna, whose orbit cannot be fully explained by known gravitational influences. What is uncertain is whether that anomaly reflects the presence of a large unseen planet, an encounter with a passing star in the early solar system, some other mechanism not yet identified, or simply the expected behavior of a population we have sampled too sparsely to understand. The search continues. Each new extreme trans-Neptunian object discovered adds a data point to the clustering analysis. Each new object found in a region of sky not previously well surveyed either strengthens or weakens the case for the bias hypothesis. The Vera Rubin Observatory Survey, expected to find dozens or hundreds of new extreme objects over its operational lifetime, may finally provide a sample large enough to resolve the question. Or it may find Planet 9 directly, a slow-moving point of light in the outer darkness that has been there all along, circling the sun on its long cold orbit, waiting to be seen. Or it may find nothing, and the clustering may dissolve as the sample grows, and Planet 9 will join the long list of predicted but unconfirmed bodies in the history of solar system science, a compelling hypothesis that the data ultimately could not sustain. What this uncertainty means, sitting quietly beneath the technical details of the orbital statistics and the survey completeness arguments, is something simple and somewhat vertiginous. We do not know whether our own solar system contains a planet, not a hypothetical planet in a distant star system, not a world orbiting some other sun light years away, but a planet orbiting our sun, in our solar system, sharing our cosmic neighborhood, potentially larger than Earth, potentially as massive as Neptune. We do not know if it is there, and we cannot currently find out because it is too far away, too dark, and too slow-moving for any existing instrument to definitively confirm or rule out. The solar system we thought we knew completely enough to name and number, 8 planets, familiar and cataloged, may contain a 9th member that has been circling silently in the outer darkness for the entire history of human civilization. Every night sky that any human being has ever looked up at may have contained, somewhere in the dark beyond the visible planets, a world we never knew to look for and have not yet managed to find. That thought is not a dramatic one. It does not arrive with urgency or alarm. It settles slowly, like the cold. Beyond the proposed orbit of Planet 9, beyond even the most distant objects we have ever directly detected, the solar system does not end. It continues outward into a region so vast and so poorly illuminated that no instrument ever built has detected a single object within it in situ. No spacecraft has crossed it. No telescope has resolved it. No survey has cataloged its contents. It exists, in the current state of human knowledge, entirely as an inference, a shape drawn not from observation, but from the behavior of things that occasionally fall inward from it, like messages arriving from a place the messenger cannot describe. This region is called the Oort cloud, and it may be the largest structure associated with our solar system. The idea emerged in 1950 from a Dutch astronomer named Jan Oort, working at Leiden Observatory in the Netherlands. Oort had been studying long-period comets with orbital periods of hundreds or thousands or tens of thousands of years, comets that appear in the inner solar system once in recorded history, and then retreat back into the dark, not to return within any human time frame. He noticed two things about these comets that the existing models of solar system dynamics could not easily explain. The first was their orbital periods. Many long-period comets arrived from distances suggesting they had originated at roughly 20,000 to 100,000 astronomical units from the Sun. Distances so extreme, they placed their source region far outside anything previously considered part of the solar system. The second was their distribution across the sky. Unlike the planets and the Kuiper Belt objects, which orbit in or near the ecliptic plane, the flat disk defined by Earth's orbit around the Sun, long-period comets arrived from all directions, from above the ecliptic plane and below it, from every compass point, uniformly distributed across the full sphere of the sky, as if they originated in a structure that surrounded the solar system on all sides, rather than lying in a flat ring around it. Oort proposed that the solar system was enclosed within an enormous spherical shell of icy bodies, the frozen remnants of the original protoplanetary disk, scattered outward over billions of years by gravitational interactions with the giant planets. This shell, he argued, extended from perhaps 2,000 astronomical units out to perhaps 100,000 astronomical units or beyond. It was roughly spherical rather than flat, because over billions of years, the gravitational influence of passing stars and the general tidal pull of the galaxy had gradually randomized the orbital inclinations of the objects within it, lifting them out of the ecliptic plane and distributing them across the full sphere. Consider what those numbers mean in practice. 1 astronomical unit is 93 million miles, the distance from Earth to the Sun. The proposed outer boundary of the Oort cloud sits at perhaps 100,000 astronomical units. That is 100,000 times the distance from Earth to the Sun. In miles, the figure requires so many digits that it loses meaning. In light travel time, it is more tractable but not more comforting. Light from the Sun crossing the distance to the Oort cloud's outer boundary takes roughly 1.6 years to arrive. The Oort cloud may extend nearly 2 light years from the Sun in every direction. To put this in human terms, the nearest star to our Sun, Proxima Centauri, sits approximately 4.24 light-years away. The proposed outer edge of the Oort cloud reaches perhaps 1.6 light-years out. The solar system, if the Oort cloud is included in its boundaries, extends more than a third of the way to the nearest star. The space between solar systems is not empty interstellar void, punctuated by discrete, well-separated systems. It may be a region where the outermost fringes of neighboring stellar systems intermingle, where the cometary populations of different suns drift through the same cold dark, weakly bound to their respective stars, occasionally perturbed into long falling paths toward the inner warmth. The Oort cloud has never been directly observed. Not one single object has been detected within it at its actual location. Every piece of evidence for its existence is indirect, drawn from the behavior of comets that have fallen inward, been accelerated by the Sun's gravity, grown their characteristic tails as solar radiation boiled away their volatile ices, and then either continued outward again on their long return journeys or been captured into shorter orbits by gravitational interactions with the planets. The comets are the messengers. The cloud they came from has never been seen. What sends them inward is itself invisible. The Oort cloud sits so far from the sun that the sun's gravitational grip on its contents is extraordinarily weak, far weaker than the grip that holds the planets and even the Kuiper Belt objects in their relatively stable orbits. At those distances, other gravitational influences become significant. The gravity of passing stars, drifting through the galaxy on their own slow paths, can tug at the loosely bound objects in the Oort cloud, nudging them onto slightly different orbits. The galactic tide, the differential gravitational pull of the galaxy's mass across the diameter of the solar system, exerts a gentle but persistent torque on Oort cloud objects, gradually altering their orbital orientations over millions of years. A molecular cloud drifting through the galaxy, or the gravitational disturbance created by the solar system's periodic passage through the denser regions of the galactic disk, can trigger what astronomers call a comet shower, a period of enhanced delivery of Oort cloud objects into the inner solar system, lasting millions of years. These mechanisms are well understood theoretically. The mathematics of stellar perturbation and galactic tides is established physics, but the objects being perturbed have never been observed in their resting state, in their home region, before the perturbation that sends them inward. We know the messengers. We do not know the country they came from. We infer its existence, its extent, its population, entirely from the properties of the occasional object that falls out of it and passes briefly through the warmth of the inner solar system before retreating again into the dark. How many objects does the Oort cloud contain? The estimates vary widely because the estimates are themselves inferences built on other inferences. A commonly cited figure is roughly 1 trillion objects larger than a kilometer in diameter. 1 trillion icy bodies, ranging in size from small rocks to objects the size of cities or larger, distributed across a spherical shell that surrounds the solar system in every direction. 1 trillion. And the Oort cloud, at its distances, is so cold that these objects have been in a state of deep freeze since the early solar system. Their surfaces have been processed by cosmic rays and interstellar radiation over 4.5 billion years, developing the same dark organic crusts that coat Kuiper Belt objects. They float in the dark, barely moving relative to the sun, loosely bound, patient in the way that only things operating on geological timescales can be patient. The inner edge of the Oort cloud, the region closest to the sun, sometimes called the Hills cloud or inner Oort cloud, may begin at roughly 2,000 to 5,000 astronomical units. This is territory that even the most optimistic projections for the Vera Rubin Observatory cannot fully survey. At those distances, the objects are simply too faint, too cold, too slow-moving to register clearly against the background sky. A kilometer-sized Oort cloud object at 5,000 astronomical units reflects so little sunlight that detecting it would require an instrument far more sensitive than anything currently planned or funded. The inner Oort cloud will remain observationally inaccessible for the foreseeable future, not because it is exotic or poorly understood in principle, but because it is dark and far, and the photons it reflects arrive in quantities too small for current or near-future technology to collect. And yet, it is there. The comets confirm it. Every long-period comet that sweeps through the inner solar system, Hale-Bopp crossing the sky in 1997, bright enough to see with the naked eye for weeks, Comet Hyakutake grazing near the Earth in 1996, the occasional brilliant visitor that appears once in a lifetime and then retreats for thousands of years. Each one is a traveler from this invisible country, a piece of the primordial solar system falling briefly through the warmth before returning to the cold. They carry the chemistry of the early solar system in their ices: water, carbon dioxide, carbon monoxide, complex organic molecules, the raw ingredients of the same processes that eventually produce life on Earth. They are old in a way almost nothing else in the accessible solar system is old, untouched, preserved, arriving from a place no instrument has ever seen. The Oort cloud is the solar system's outermost atmosphere, a vast, tenuous spherical envelope of frozen material that surrounds everything we have ever known, everything we have ever explored, everything we have ever mapped, and extends outward into the dark in every direction until the sun's gravity grows too weak to hold it, and the objects within it drift free into interstellar space, no longer belonging to any star. We have never seen it. We have only felt its breath in the form of the comets it occasionally releases, falling inward across billions of miles of cold and silence to pass briefly through the sky. And beyond even the Oort cloud, the solar system truly ends. But the ending is not a wall. It is a gradual loosening, a slow release. The boundary between what belongs to the sun and what belongs to the galaxy is not a line, but a fading, a region where the sun's influence thins so gently that no spacecraft could feel the moment of crossing. There is no edge to pass through. There is only the increasing distance and the increasing cold and the increasing certainty that the familiar map has run out of territory. The largest structure associated with our solar system remains entirely invisible to us. It surrounds us completely. It has always been there, and we know it only as an absence, a source region that reveals itself only when something falls out of it. What limits our knowledge of the Oort cloud is not, at its core, a matter of ambition. It is a matter of instruments, of detection floors and survey sensitivity, and the physical limits of what current and near-future technology can see. And those limits, as profound as they are for the Oort cloud, are not unique to the outermost regions. They apply in varying degrees across the entire outer solar system. The tools we use to see beyond Neptune are not just limited. In certain important respects, they are almost blind. Every piece of knowledge assembled in the previous sections, the Kuiper Belt's partial catalog, the orbital clustering that hints at Planet 9, the inferred existence of the Oort cloud, arrived through instruments, telescopes on mountaintops in Chile and Hawaii and Arizona, detectors cooled to temperatures just above absolute zero to reduce the thermal noise that would otherwise drown out the faint signals from the outer dark. Software pipelines that compare images taken nights or weeks apart, flagging anything that moves against the fixed background of distant stars and galaxies. These are the tools through which the outer solar system has been assembled, piece by piece, object by object, into the incomplete portrait we currently hold. And every one of those tools has a floor, a threshold of sensitivity below which the signal from a distant object simply cannot be distinguished from noise, a limiting magnitude, a measure of faintness, beyond which the instrument cannot go, regardless of how long the exposure runs or how carefully the data is processed. The floor is not arbitrary. It is not a matter of engineering that better funding or better design could simply push aside. It reflects, in part, genuine physical constraints on what instruments of a given size and sensitivity can detect when the thing being detected is a dark, cold, slowly moving body at billions of miles from the sun. Understanding where those floors are and why they exist where they do is the same as understanding the shape of our ignorance about the outer solar system. The most fundamental method for detecting outer solar system objects is the one that finds almost everything in the current catalog: reflected visible light. A telescope collects photons that the sun has sent outward that have traveled across hundreds of millions or billions of miles to strike the surface of a distant object, and that have then been reflected back across the same distance toward Earth. The telescope's mirror gathers these photons over an exposure period that might range from seconds to hours, and the accumulated signal is compared against the background sky to identify the object. The efficiency of this method depends on three things: the size of the telescope's mirror, which determines how many photons can be collected in a given time; the sensitivity of the detector, which determines what fraction of arriving photons are actually recorded; and the brightness of the object itself, which depends on its size, its distance, and its albedo, the fraction of incident sunlight it reflects back. Of these three, the telescope mirror and the detector are things engineers can improve. The brightness of the object is not. It is fixed by the physics of the inverse square law and the surface properties of the object itself. And as Section 3 established, the brightness of outer solar system objects falls catastrophically with distance. An object at 100 astronomical units is not merely twice as hard to detect as one at 50 astronomical units. It is 16 times harder because the inverse square law applies twice, once for the sunlight traveling out to the object and once for the reflected light traveling back. 16 times harder to detect. For an object at 200 astronomical units, the factor rises to 256. At 500 astronomical units, it is nearly 40,000. The world's largest optical telescopes, currently the Twin Keck telescopes in Hawaii and the Very Large Telescope array in Chile, with mirrors ranging from 8 to 10 meters in diameter, can detect outer solar system objects to a certain limiting magnitude in a reasonable exposure time. The Vera Rubin Observatory, with its 8.4 meter mirror and its extraordinarily wide field of view, will push that limit somewhat deeper. But even Rubin has a floor. Objects below a certain brightness, objects too small, too dark, or too distant, will not appear in its images regardless of how many times it photographs the same patch of sky. For the classical Kuiper Belt, this floor is a manageable limitation. Most of the larger objects in the belt, those hundreds of kilometers across, are bright enough and close enough to appear in current or near future surveys. The population of smaller objects, those tens of kilometers across or less, is largely invisible to existing instruments, but the larger members of the population give a statistical basis for estimating the small object population through size distribution models. The picture is incomplete, but not entirely dark. For the scattered disk and the detached objects like Sedna, the floor becomes more constraining. These objects are farther out, more sparsely distributed, and their orbits carry them to distances where reflected light drops to levels that strain the sensitivity of current surveys. The catalog of known scattered disk objects is almost certainly missing a significant fraction of the actual population. How large a fraction is genuinely unknown, because estimating the missing population requires assumptions about the orbital distribution that cannot be verified without finding more objects. For the hypothetical inner Oort cloud, the Hills cloud, beginning at perhaps 2,000 to 5,000 astronomical units, existing and planned instruments are essentially blind. A kilometer-sized object at 5,000 astronomical units reflects so little sunlight that even a 30-meter telescope, the largest currently under construction, would struggle to detect it in any reasonable exposure time. The proposed extremely large telescope, currently being built on a mountaintop in Chile's Atacama Desert, with a primary mirror 39 meters in diameter, the largest optical telescope ever constructed, will represent the most powerful ground-based eye humanity has ever turned on the sky, and the inner Oort cloud will still be largely invisible to it, not because the telescope is inadequate by the standards of its engineering, but because the objects are too far, too dark, and the photons too few. There is a second detection method that works differently from reflected visible light, and that offers a partial complement to optical surveys in certain cases. Thermal infrared detection. Every object with a temperature above absolute zero emits thermal radiation, heat in the infrared portion of the spectrum. Cold outer solar system objects sitting at temperatures of perhaps 30 to 50 degrees above absolute zero emit faintly in the far infrared. Space-based infrared telescopes operating above Earth's atmosphere, which absorbs much of the relevant infrared wavelengths, can in principle detect this thermal emission from objects that might be difficult to find in reflected visible light, particularly if the objects are dark and therefore reflect little but are large enough to emit measurable heat. The WISE mission and its successor, NEOWISE, conducted infrared surveys of the sky between 2010 and 2020 and cataloged thousands of solar system objects, including many in the outer regions. But thermal infrared detection has its own flaw. Colder objects emit less radiation and at longer wavelengths that require increasingly specialized detectors. Objects in the inner Oort cloud, at temperatures approaching 30 Kelvin, roughly negative 405 degrees Fahrenheit, are near the practical detection limit for any currently planned infrared space telescope. The next generation of space-based observatories may push this limit somewhat, but the physics of cold body radiation sets a floor that engineering can approach but not eliminate. A third method, rarer but in principle capable of detecting objects that visible and infrared surveys miss, is stellar occultation. When a solar system object passes in front of a background star, it briefly blocks the star's light, a dimming event that can last anywhere from a fraction of a second to several seconds, depending on the object's size and distance and the geometry of the alignment. By monitoring large numbers of background stars continuously and watching for these brief dimmings, astronomers can, in principle, detect outer solar system objects, even if the objects themselves are too faint to see directly. The Taiwanese American Occultation Survey and similar programs have used this technique to probe the population of small Kuiper Belt objects, finding members of the population that are far too small to be detected by reflected light surveys. The technique works, but it is statistically demanding. The probability that any given object will occult any given star during any given observation window is extremely small, and building a useful sample requires monitoring millions of stars for years. What all of this amounts to is a picture of detection capability that is genuinely impressive by historical standards. Surveys that would have seemed like science fiction to the astronomers who spent decades without finding a single Kuiper Belt object, and genuinely limited by the standards of what the outer solar system requires. The instruments are remarkable. The territory is more remarkable. The gap between them is the shape of our ignorance. New Horizons, the only spacecraft currently traveling through the outer solar system beyond Saturn, represents a different kind of instrument entirely. Not a remote observer collecting photons from billions of miles away, but an in situ probe, physically present in the region it is studying, able to measure things that no Earth-based telescope can reach. Its instruments detected the solar wind, the charged particle environment, the dust density, properties of the outer solar system that are invisible to optical and infrared surveys. Its cameras resolved the surfaces of Pluto and Arakoth at resolutions that no telescope could approach from Earth. But New Horizons is one spacecraft on one trajectory. It samples a single narrow corridor through a vast and three-dimensional region. The knowledge it generates is extraordinarily detailed along its specific path, and essentially zero everywhere else. Sending a fleet of New Horizons-class spacecraft in multiple directions through the outer solar system would address this limitation. But each mission requires decades of travel time and hundreds of millions of dollars, and the corridors they would sample would still represent a vanishingly small fraction of the total volume. The instrumentation wall is real. It is not a temporary obstacle that the next generation of telescopes will simply overcome. It is a boundary defined by the physics of light and distance and thermal emission that recedes as instruments improve, but never disappears. Every new survey pushes the frontier outward somewhat. Every new telescope sees a little deeper. But the outer solar system is deep in a way that ensures the frontier always remains. The territory beyond the instruments is always larger than the territory within them. And the instruments themselves are only one kind of limitation. There is another kind, one that operates not in the realm of photons and mirrors and detector sensitivity, but in the realm of time, a blindness that no instrument, however powerful, can fully correct. There's a sense in which every telescope is a time machine, not in the dramatic sense of science fiction, not a device that transports its operator backward or forward through history, but in the quieter, more literal sense that every photon a telescope collects left its source at some point in the past. The light arriving at the mirror right now departed its origin some time ago. For objects in the inner solar system, this delay is trivial. Sunlight reflected from the moon left the lunar surface roughly 1.3 seconds ago. Light from Mars, at average distances, is perhaps 12 minutes old when it arrives. These delays are real but inconsequential for most purposes. They do not meaningfully affect what we know about those objects or how we observe them. But the outer solar system is not the inner solar system. Light reflected from a Kuiper Belt object at 40 astronomical units left that object roughly 5.5 hours ago. By the time it reaches a telescope on Earth, the object has moved, very slightly, imperceptibly to casual inspection, but measurably to a precise instrument. Light from a hypothetical Planet 9 at 600 astronomical units would be roughly 3.5 days old on arrival. Light from an inner Oort cloud object at 5,000 astronomical units would have been traveling for nearly 3 months before it reached the mirror. In isolation, these delays are interesting but not particularly consequential. The outer solar system moves slowly. An object at 40 astronomical units completes one orbit of the Sun in roughly 250 years. In 5.5 hours, it has moved a distance so small relative to the circumference of its orbit that no practical observation would be affected by the light travel delay alone. The time machine aspect of the telescope does not, by itself, create a serious epistemological problem for outer solar system science. The problem arrives not from the light travel time of individual observations, but from the time required to conduct surveys. The accumulated delay between when a region of sky is observed and when the full picture of what it contains can be assembled. And this problem compounds with distance in a way that mirrors, and in some respects exceeds, the problem of the detection floor. Consider how outer solar system objects are found. A telescope photographs a patch of sky. Days or weeks later, it photographs the same patch again. The two images are compared. Everything that stayed in the same position between exposures is a background star or galaxy, fixed, distant, unmoving on human timescales. Anything that shifted position is a solar system object moving along its orbit between the two observation dates. The size of the shift, combined with the time elapsed and the geometry of the observation, gives a preliminary estimate of the object's distance and orbital characteristics. For objects in the classical Kuiper Belt, this technique works reasonably well. An object at 40 astronomical units moves enough between observations separated by a few days to be detectable as a mover against the background sky. The shift is small, a few arc seconds, a fraction of the width of a full moon, but it is measurable with current instrumentation, and the technique has produced the bulk of the known Kuiper Belt catalog. But at greater distances, the apparent motion of an object across the sky decreases, not linearly, but steeply. An object's angular velocity, the rate at which it appears to move across the sky as seen from Earth, falls roughly with the inverse of its distance from the Sun, modified by the geometry of the observation and the object's actual orbital velocity. An object at 100 astronomical units moves across the sky at roughly 1/4 the angular rate of an object at 40 astronomical units. An object at 500 astronomical units moves at perhaps 1/12 the rate. An object at 2,000 astronomical units in the inner Oort cloud moves so slowly that distinguishing its motion from the proper motion of background stars. The genuine slow drift of stars across the sky over years and decades due to their own motion through the galaxy becomes technically demanding. To put this in human terms, an inner Oort cloud object at 5,000 astronomical units, observed twice with a separation of 1 month between exposures, would have moved across the sky by an amount roughly equivalent to the apparent diameter of a human hair held at arm's length. Not impossible to measure with the most precise current instruments, but at the edge of what is practical, requiring exquisite calibration and careful subtraction of every other source of apparent motion in the image. What this means in practice is that finding objects in the outer reaches of the solar system requires either extraordinary positional precision over short time baselines or observations separated by months or years to accumulate a detectable shift. And observations separated by months or years introduce their own complications. The sky survey that conducted the first observation may have moved on to other targets by the time the follow-up observation is needed. The telescope may have been reassigned. The funding cycle may have shifted. The same patch of sky may be in a different position relative to the galaxy's dense central plane, changing the background star density and complicating the comparison. A survey that was designed with a cadence optimized for finding near-Earth asteroids or classical Kuiper Belt objects may simply not revisit the same field on the timescales required to detect motion in the outer regions. This is not a hypothetical problem. It has affected real discoveries. Sedna was found during a survey specifically designed to look for distant objects, using a wide-field camera and a detection pipeline optimized for slow movers. Most surveys of the time were not so configured. Had Sedna's discovery been left to the standard programs of the era, it might have been missed entirely. A slow point of light that appeared once in a survey image was not flagged as a mover because the follow-up observation came too late or too soon, and was quietly filed as an unidentified background object. The survey incompleteness problem has a temporal dimension that is distinct from, and in some ways more difficult to address than, the photon counting problem of the detection floor. A larger telescope mirror solves the photon problem. More mirror area means more photons collected per unit time, pushing the detection floor to fainter magnitudes. But a larger mirror does not solve the cadence problem. An object that moves too slowly to be identified as a mover in a survey with a given revisit interval will remain unidentified regardless of how powerful the telescope becomes, unless the survey strategy itself is redesigned to include longer time baselines for the outer regions. The Vera Rubin Observatory's LSST survey has been designed with some attention to this problem. Its cadence strategy includes provisions for detecting slow-moving outer solar system objects, and its 10-year operational baseline means that objects requiring years of observation to establish a reliable orbit can, in principle, be tracked from first detection through full orbital characterization within the survey's lifetime. This is a genuine improvement over previous programs, but the cadence is still optimized across a large number of competing scientific priorities. The survey is doing many things simultaneously, mapping billions of galaxies and monitoring variable stars and searching for near-Earth asteroids, all with the same telescope and the same finite observing time. The outer solar system is one priority among many. And beyond the survey cadence problem lies a still deeper temporal issue. The outer solar system is not static. It is evolving, slowly on human timescales, but genuinely and measurably over the longer periods that solar system science must sometimes consider. Objects are being perturbed by passing stars and galactic tides. Orbits are shifting. Objects that are currently near perihelion their closest approach to the sun, and therefore most detectable, will retreat outward over centuries and millennia. Objects currently too far out to detect may be falling inward toward their next perihelion passage over timescales of thousands of years. The snapshot that any survey takes of the outer solar system is a snapshot of where things happen to be right now, in this particular century, at this particular moment, in the solar system's 4.5 billion year history. What this means is that the outer solar system we observe is not necessarily representative of the outer solar system as it typically exists. We are sampling one moment, one configuration, one arrangement of orbits out of the enormous range of configurations that the outer solar system passes through over geological time. Some objects that belong to the outer solar system's long-term population are currently in positions where they cannot be detected. Some objects that are currently detectable will retreat beyond detection within centuries. The survey is not just spatially incomplete, it is temporally incomplete as well. A single frame from a film that runs for billions of years, presented as if it were the whole story. All of this accumulates into a picture of outer solar system knowledge that is, at its foundation, a picture of what happens to be detectable right now from Earth, using instruments of a certain size and sensitivity, with survey strategies of a certain cadence and sky coverage, at this particular moment in the solar system's long history. It is not a picture of what is there. It is a picture of what is visible. And the gap between those two things, between what is there and what is visible, is the measure of our ignorance. That ignorance has a shape. It is not random. It is not uniformly distributed across the outer solar system. It clusters at the faint end of the magnitude distribution. It deepens with distance. It thickens in the regions of sky where surveys have been sparse. It concentrates in the orbital populations that move most slowly and require the longest time baselines to characterize. The shape of our ignorance is, in a certain light, as informative as the shape of our knowledge. And what the shape of our ignorance tells us, if we look at it carefully, is something specific about what we are probably missing and what that missing population might mean. Science is usually described as the accumulation of what is found, the catalog of discovered things growing longer over time, each new object adding a data point to the picture, each new survey pushing the frontier outward. This is accurate as far as it goes, but there is another kind of knowledge that science generates, quieter and less celebrated, that comes not from what is found, but from what is not found, from the specific structured shape of the absence, from the silence of the surveys, and what that silence, carefully examined, reveals about the territory it covers. The outer solar system has generated a great deal of this second kind of knowledge, and some of what it has revealed is more unsettling, in a quiet way, than anything the cataloged objects have shown. Begin with the missing mass, the standard models of solar system formation, the computational simulations that track the behavior of the protoplanetary disk from its earliest stages through the gradual accumulation of planetesimals into planets, predict that the outer solar system should contain significantly more material than is currently observed. The disk that surrounded the young sun was not uniform. It was denser in some regions than others, and the density distribution shaped where planets formed and how large they grew. The models that best reproduce the current configuration of the giant planets, Jupiter, Saturn, Uranus, Neptune, in their current orbits with their current masses, generally require a disk that contained considerably more material in the outer regions than is accounted for by the known Kuiper Belt population. Where did it go? This is a genuine open question in planetary science, and the answers proposed range from the plausible to the speculative. One possibility is that the early solar system underwent a period of dynamical instability, a phase perhaps triggered by gravitational interactions among the giant planets themselves, in which the outer solar system was violently reorganized. In this scenario, the original population of outer solar system bodies was far larger than what we observe today, and the instability scattered much of it outward into interstellar space or inward into the sun. The NICE model, named for the French city where the researchers who developed it were based, proposes a version of this scenario in which the giant planets migrated significantly from their original orbital positions, scattering the primordial outer disk in the process. What this means in practice is that the Kuiper Belt we observe today may be a remnant, a depleted, scattered survivor of a population that was once far more massive and far more densely populated. The missing mass is not in the outer solar system anymore. It was ejected. It is gone. The sparse, cold belt beyond Neptune is what remains after billions of years of gravitational processing removed the bulk of the original material. But this scenario, compelling as it is in many respects, is not the only possibility. And even if it is broadly correct, it does not account for everything the surveys are not finding. There remain specific populations of objects, predicted by the models, expected by the theory, that have not appeared in the numbers the models suggest they should. Consider the population of objects in very distant, highly inclined orbits. The scattered disk and the detached population should, according to several formation models, contain a significant number of objects on orbits that carry them to extreme distances and high inclinations, orbits tilted steeply relative to the ecliptic plane, objects that spend most of their time far above or far below the flat disk where surveys are typically most sensitive. These objects are expected to exist in significant numbers. They have not been found in those numbers. Either the models are wrong, or the surveys are missing them, or both. The surveys are almost certainly missing many of them. Objects in highly inclined orbits spend much of their time far from the ecliptic plane, in regions of sky that most surveys cover poorly. A survey optimized to find Kuiper Belt objects moving slowly near the ecliptic, will naturally be less sensitive to objects that happen to be passing through high ecliptic latitudes during the survey window. The incompleteness is not random. It is geometrically structured. It is the shape of the telescope's preferred viewing zone impressed upon the catalog of known objects. Beyond the missing populations predicted by formation models, there is a more exotic category of absence that has attracted attention in recent years. The outer solar system may contain objects that did not originate in our solar system at all. In 2017, an object designated Oumuamua passed through the inner solar system on a trajectory that was unmistakably hyperbolic. It was moving too fast to be gravitationally bound to the sun. It had come from interstellar space. It was the first confirmed interstellar object ever detected passing through the solar system. Its properties were strange. It was elongated, or perhaps flat, tumbling as it moved, showing no cometary activity despite passing close to the sun, exhibiting a slight acceleration that could not be explained by solar gravity or radiation pressure alone. It departed the solar system before anyone could study it properly, and the debate about its nature, natural object, unusual comet, something else, continues. In 2019, a second interstellar object, Borisov, was detected. This one was more conventional, a comet, showing the expected activity, with a composition broadly similar to solar system comets. It too passed through and departed. 2 interstellar objects detected in the space of 2 years, after decades of surveys that found nothing of the kind. The implications are not dramatic, but they are worth sitting with. If interstellar objects pass through the solar system frequently enough to have been detected twice in the first years of surveys, sensitive enough to find them, then the actual flux of such objects through the solar system is likely significant. Most pass through undetected. Most are too small or too dark or too distant from Earth's orbit to register in any survey. Some, moving slowly enough near the sun, may have been gravitationally captured, may have transitioned from interstellar trajectories to loosely bound solar orbits, and now reside in the outer solar system, unrecognized, cataloged perhaps as unusual Kuiper Belt objects, or Oort cloud members without any indication of their true origin. The outer solar system may contain interstellar immigrants. Objects that formed around other stars were ejected during the dynamical evolution of those systems, drifted through the cold interstellar medium for millions or billions of years, and were eventually captured by the sun's gravity during a slow passage through the outer reaches of the solar system. These objects would carry in their composition the chemical signature of a different stellar environment, different isotope ratios, different volatile inventories, different surface processing histories. They would be, in a sense, messages from other solar systems, sitting in the outer dark alongside the native population, indistinguishable from our current survey data. We would not know they were there. We do not have the tools, at present, to identify a captured interstellar object by remote observation alone. The distinction would require in situ analysis, a spacecraft close enough to sample the object's composition and compare it against what solar system formation models predict. That kind of analysis, for most of the outer solar system population, is not available and will not be available for the foreseeable future. And beneath all of these specific absences, the missing mass, the incomplete high inclination population, the possible interstellar immigrants, lies the most fundamental absence of all: the absence of knowledge about what categories of objects remain entirely unconceived. The history of outer solar system science is a history of surprises. The Kuiper Belt was predicted theoretically, but its actual properties, when it was found, differed in important ways from the predictions. Pluto's geology, when New Horizons revealed it, was more complex and more active than almost anyone had expected. Oumuamua's properties did not fit cleanly into any existing category. Sedna's orbit has no fully satisfying explanation. Each surprise was a reminder that the models are built from a limited sample, that the extrapolations from the known to the unknown carry genuine uncertainty, and that the outer solar system is under no obligation to conform to the picture that the inner solar system and the available data have led us to construct. What we are not finding may include entire populations of objects in orbital configurations the current models do not predict. Objects in retrograde orbits, circling the sun in the opposite direction from the planets, perturbed into those unusual paths by mechanisms not yet identified. Objects in polar orbits, crossing the ecliptic plane twice per orbit, difficult to detect because they spend most of their time far from where surveys look. Objects too small to detect individually, but contributing collectively to the mass budget in ways that affect the gravitational environment of the outer solar system. Objects in the process of transitioning between populations, scattered outward from the Kuiper Belt toward the Oort cloud, or falling inward from the Oort cloud toward the scattered disk, caught in the middle of journeys that take millions of years and that our survey baseline of a few decades cannot follow. The catalog of known outer solar system objects is a catalog of what happens to be detectable in orbits that happen to bring objects close enough to the sun to reflect measurable light at this particular moment in history. It is a sample. The sample is real. The knowledge it contains is genuine, but it is a window, not a wall, and the darkness beyond the window is not empty, it is simply dark. And in the outer solar system, darkness and absence are not the same thing. They have never been the same thing. They only appear that way from a distance, to instruments that are still learning to see. There is a pattern in the history of human knowledge about the cosmos that repeats so consistently it has almost become invisible through familiarity. A boundary is drawn. The boundary represents the edge of what is known, the limit of what current instruments and current understanding can reach. For a time, sometimes decades, sometimes centuries, the boundary is treated not merely as the edge of knowledge, but as something closer to the edge of reality. The unknown territory beyond it is assumed to be empty or uniform or unimportant because the tools available to examine it return nothing, and nothing is easy to interpret as absence. And then the tools improve, and the boundary moves, and what was assumed to be empty turns out to be full of structure, full of objects, full of processes that were always there and simply waiting for an instrument sensitive enough to reveal them. This has happened so many times in the history of astronomy that it has acquired the character of a law. The flat Earth gave way to the spherical one. The spherical Earth at the center of the cosmos gave way to a sun at the center of the solar system. The solar system, assumed to be the entirety of creation, gave way to a galaxy of hundreds of billions of stars. The galaxy, assumed to be the universe, gave way to a cosmos of hundreds of billions of galaxies, each containing hundreds of billions of stars, stretching outward in every direction to distances that make the solar system seem like a dust grain on the floor of an empty cathedral. Each expansion of the boundary revealed not a simpler picture, but a more complex one. Not fewer questions, but more. Each time the map grew larger, the territory it described turned out to be stranger and more varied than the map that preceded it had suggested. The history of cosmology is not a history of answers accumulating toward a final complete picture. It is a history of questions deepening, of each answer opening a larger space of uncertainty than the one it closed. The outer solar system is the current instance of this pattern. The boundary drawn at Neptune held for most of the 20th century. It has since moved considerably through the Kuiper Belt discoveries and the detection of scattered disk objects, and Sedna and the theoretical elaboration of the Oort cloud. The boundary is now somewhere in the inner Oort cloud, at distances where current instruments cannot reliably see. Beyond it lies the outer Oort cloud, the boundary where the sun's gravity fades, the interstellar medium, the long cold dark between solar systems. The pattern suggests that when instruments improve enough to push the boundary outward again, what is revealed will be more complex and more surprising than current models predict. But the pattern also suggests something quieter and perhaps more important. It suggests that the boundary is a property of the instruments, not of the territory. The edge of what is known is not the edge of what exists. It never has been. Every boundary that has ever been drawn around the known cosmos has turned out to describe the limits of the technology available at the time it was drawn, not the limits of what was actually there. What this means for the outer solar system is not that we should expect dramatic discoveries, though we should and will as surveys improve. It means that the current picture, as carefully assembled and as genuinely informative as it is, describes a fraction of what is there, and the fraction is not large. The Kuiper Belt catalog represents perhaps a few percent of the objects it contains. The scattered disk and detached populations are more poorly characterized still. The inner Oort cloud is observationally inaccessible. The outer Oort cloud is known only through inference. The total population of the outer solar system, the true census, the actual count of everything that orbits the sun beyond Neptune, is unknown and will remain unknown for longer than any currently living person will be alive to see the answer. This is not a failure. It is a boundary condition. It is the shape of the problem. Consider the Voyager spacecraft. 2 machines launched in 1977, carrying gold-plated records encoded with sounds and images from Earth, greetings in 55 languages, music from Bach to Chuck Berry, the sound of rain and wind and surf, photographs of human beings and human structures, and the planet they came from. The records were placed aboard not because there was any realistic expectation that they would be found, but because the gesture seemed right. Because sending something outward into the dark without any acknowledgement of the civilization that built it felt incomplete. Because the humans who designed Voyager wanted to mark the occasion of humanity's first deliberate crossing into interstellar space with something that expressed what humanity was. Voyager 1 is now more than 23 billion miles from the sun. Its signal, traveling at the speed of light, takes more than 22 hours to reach us. It is the most distant human-made object in existence, and it is, in the context of the outer solar system's true extent, extraordinarily close. It has barely crossed the boundary of the heliosphere, the region where the sun's solar wind gives way to the interstellar medium. The inner Oort cloud begins at perhaps 2,000 astronomical units. Voyager 1 is currently at roughly 160 astronomical units. To reach the inner Oort cloud at its current velocity, roughly 38,000 miles per hour, the fastest any human artifact has ever traveled, would take approximately 300 years. To cross the Oort cloud entirely and reach interstellar space in the fullest sense would take tens of thousands of years. No human institution has ever survived tens of thousands of years. No spacecraft has ever been designed to operate for centuries. The outer solar system is not merely beyond the reach of current instruments. It is beyond the reach of any civilization that operates on human timescales, plans on human timescales, funds missions on human timescales. It is outside the envelope of what organized human effort can practically accomplish, not because the physics forbids it, but because the distances are simply larger than the duration of civilizations. The comets understand this in their way. A long-period comet, perturbed from the Oort cloud by the gravitational nudge of a passing star, begins its inward journey from perhaps 50,000 astronomical units. It falls toward the sun for millions of years. It crosses the orbits of the outer planets. It enters the inner solar system, grows its tail, blazes briefly in the night sky, and then retreats again on an orbit that will carry it outward for millions more years before it returns. Its journey from the Oort cloud to perihelion takes longer than modern humans have existed. Its round trip takes longer than the interval since the extinction of the dinosaurs. It moves on timescales that make the entire history of human civilization invisible. A brief flicker, a momentary warmth, somewhere along the arc of its long, cold path. We observe the comet. We measure its composition, its orbit, its brightness. We infer from its properties something about the region it came from, the cold, dark, distant reservoir that launched it inward millions of years ago. We hold this inference carefully, knowing it is an inference, knowing it describes a place we have never seen and may never see. And then the comet departs, and the inference is all that remains. This is the outer solar system's relationship to human knowledge. It communicates through messengers, through the occasional comet, through the faint and slow-moving points of light that appear in long exposure survey images, through the statistical clustering of orbital orientations that hints at an unseen gravitational influence, through the anomalous orbit of a single distant world that no current model can fully explain. The outer solar system does not present itself for examination. It leaves traces, and we read them as best we can, knowing that the traces are partial, knowing that the picture assembled from them is a picture of the traces rather than a picture of the thing itself. There is a kind of humility that this enforces, not the performed humility of scientific disclaimers, the routine acknowledgement that more research is needed, but something quieter and more fundamental, a recognition that the solar system we inhabit extends far beyond the region we can see, that the map we carry is a small bright island in a much larger dark, and that the dark is not empty but simply beyond the reach of every light we have yet managed to produce. The outer solar system is not waiting to be understood. It does not exist in a state of suspension, paused until the instruments improve and the surveys extend and the models converge on a complete picture. It is present. It is real. Its objects move along their orbits right now, in the cold and the silence, as indifferent to our awareness of them as they have been for the 4.5 billion years they have been doing so. Our knowledge of them is a recent and fragile thing. A few decades of sky surveys, a handful of spacecraft trajectories, a theoretical framework assembled from a sample so small that its representativeness cannot yet be established. The outer solar system existed for billions of years before any instrument turned toward it, and it will continue for billions of years after every instrument currently imagined has ceased to function. What we have, in the end, is not a map. It is the beginning of a map, the coastline of something whose full interior has not yet been entered. And somewhere in that interior, in the cold and the vast and the dark beyond Neptune, beyond the scattered disk, beyond the theoretical boundary of the inner Oort cloud, in the long, slow distance between here and the nearest star, the solar system continues, quietly, patiently, carrying its trillion cold bodies through the dark on their long, slow orbits, indifferent to whether they are counted, indifferent to whether they are named, indifferent to whether anything, anywhere, has yet found the instruments to see them. You are listening to these words somewhere in the inner solar system, within a few light minutes of the sun, inside the warm, bright, narrow band of distance where liquid water can exist on a planetary surface, where the sun appears as a disk rather than a point, where the light arrives in quantities sufficient to drive the chemistry of living things. You are, in the context of everything this story has described, very close to the center, very close to the only part of the solar system that has ever been visited, mapped, named, or understood in any meaningful detail. Everything else is out there, in the dark beyond the last planet, in the cold beyond the scattered disk, in the invisible reservoir of the Oort cloud that surrounds the solar system in every direction, extending nearly 2 light years outward into the space between stars. Trillions of objects moving on their long, slow orbits, carrying in their frozen interiors the chemistry of the early solar system, the raw material of worlds that never quite assembled, the deep record of 4.5 billion years of cold and silence. We will not map it, not completely, not in any time frame that a civilization operating on human timescales can honestly contemplate. The distances are too great, the objects too dark, the instruments too limited, the time required too vast. Each generation of surveys will push the boundary outward a little. Each new telescope will see a little deeper. Each new mission will sample a little more of the corridor it travels through. And the outer solar system will remain, through all of it, larger than the knowledge assembled about it. The map will grow. The territory will always be larger than the map. This is not a tragedy. It is a boundary condition of existence in a solar system this size. The universe did not build the outer solar system to human scale. It built it to its own scale, which is the only scale it knows. Vast, patient, cold, and largely indifferent to whether anything, anywhere, has yet developed the instruments to examine it. There is a comet somewhere in the outer dark right now that began its inward journey before the first human being looked up at the sky and wondered what the lights were. It has been falling toward the sun for longer than civilization has existed. It will reach the inner solar system long after every institution and language and memory of this moment has dissolved. It carries in its ice the record of the solar system's earliest days, the composition of the disk, the chemistry of the young sun, the building blocks of everything that came after. It is a message from the beginning, traveling toward a reader who may not be there when it arrives. The outer solar system is full of messages like this one, falling inward on their long cold arcs, patient in the way that only geological time permits patience, carrying their contents through the dark without urgency, without destination, without any awareness of the small warm planet they are slowly approaching. We will not read most of them. We will not see most of what is out there. We will know, always, only the nearest edge of something whose full depth lies beyond us. And the dark beyond Neptune will remain what it has always been: vast, cold, present, and quietly, completely beyond our reach.